Hi, everyone. My name's Kevin. I'm a researcher at Google and a student at Columbia University. And today I'm going to be talking about our recent work on Doubly-Affine Extractors and their applications. This is a joint work with Yevgeniy Dodis, who is a professor at NYU. All right, let's get started. So today I'll be talking about the focus of our work, which is the problem of information-theoretic encryption. I'll go through some prior works that enable this, called bounded storage model extractors. And then I'll get into our contributions, which is a new form of extractors that we call Doubly-Affine Extractors, our constructions of these extractors, and then the applications of them. All right. So let's start off with information-theoretic encryption. So I'm assuming most people who are attending this conference are aware of this, but for those who aren't, at a high level, we're just doing encryption. You have a sender, you have a receiver. They both share some private key. The sender wants to encrypt the message that'll be sent to the receiver, and it does this using the private key and sends it to the receiver, and the receiver can decrypt using the private key. Simultaneously, there's some adversary who can sort of see the encryptions in the middle and try to compromise the encryptions. For information-theoretic encryption, what we really care about, like I said here, the adversary can see the information being sent from the sender to the receiver. But for information-theoretic encryption, what we're really considering are these all-powerful adversaries. So they have unlimited computational power. They're allowed to do whatever they want. So think of this as like they can run any program they want, even their favorite NP-hard problem, and solve it. But the good part about information-theoretic encryption is that it is resistant to future attacks. So any growth in computational power, the invention, or quantum computing, information-theoretic encryption remains resistant to all such improvements. All right, so since information-theoretic encryption is so powerful against even these all-powerful adversaries, there must be some sort of limitation. And this is essentially what Shannon's theorem, the famous Shannon's theorem states. Essentially, for information-theoretic encryption, the secret key must be as long as the total size of encrypted messages. So for example, if we want to encrypt all of these 4 messages, our key has to be as long as the 4 messages, essentially. All right, so this seems like a limitation, but maybe it's not. So first of all, the one thing I'd like to note is that memory is getting cheaper. So maybe storing these large keys in storage, and having them and using them only for encrypting very important messages may not be so infeasible today, and it may be very important to hide the contents of these messages. But beyond that, there's this sort of second idea that we'll actually explore very deeply in our paper, is the idea of maybe, could we outsource the key to a shared server? So for example, let's imagine we have some cloud storage server that holds this very large key. But the server, of course, has to be accessible to all parties. So that means both the senders, receivers, as well as actually the adversary. And so this solves one problem of having sort of the memory of storing this large key in memory. As we get cloud storage, we can just outsource it. But now the adversary has access to the key as well, and we'll deal with this in our paper later on. But beyond just having this large key, there are other important properties of information-theoretic encryption, and there are 3 of them that we'll go through now. So the first is being stateless. So what does it mean to be stateless? It means that in this encryption scheme, both the sender and receiver do not store any more information beyond just their private key. So okay, this seems like a weird limitation, but it turns out that if you have statefulness, where the sender and receiver can store information beyond just the private key, information-theoretic encryption is actually straightforward. So what could happen is you could, whenever you want to encrypt a message, you just XOR with a part of the key that hasn't been used before. And you can do this repetitively. If you have 4 messages, just use new parts to XOR, and that'll be the new, that'll be essentially your encryption. So this works, but the problem you can imagine is when we have, let's say, a large group of people. Let's say we have this large group of people, they all have the same private key, but they all want to simultaneously encrypt messages and send them to one another. And for example, they don't want to sort of send to the whole world that they use a specific part of their private key. And here is the point where statelessness is really important. We want to have an information-theoretic encryption where people can use the private key, even if they share them, without telling anyone they have to. And you can see now why statelessness is very important. So a very simple potential solution to try and solve this specific problem is sort of splitting up the key for each specific user. So if there's 4 users, each of them get a dedicated quarter of the private key. But there's a problem here, and the problem is that we assume that all parties encrypt the same number of messages. So for example, if one party doesn't encrypt any messages and is only decrypting, we end up losing almost a quarter of the key. And simultaneously, let's say the first user is the one who only encrypts, they're essentially unable to start to continue to encrypt messages at some point once they exhaust their part of the private key. So in an ideal world, we don't want to make this assumption. And in our work, we'll design sort of encryption schemes that don't utilize this, that are stateless, as well as do not assume anything about the number of messages that any party encrypts. All right, so let's get to the second important property of information-theoretic encryption, which is locally computable. So this one's a lot more simpler, and it's about efficiency. Essentially, let's say you have a user who wants to encrypt a message. We don't want them accessing the entire key. For example, having to load the entire key and do some computation over all of it just to encrypt a short message. So what we ideally want is actually the user to only probe maybe a small part of the key and sort of use this small portion of the key to encrypt the message. So being a little more formal, we have two locality measures that we'll consider in this paper: probe locality and cache locality. For probe locality, what we're essentially meaning is essentially the number of entries you're probing, or the number of bits you probe in the key. So here we're probing 3 entries or 3 bits. For cache locality, this is a slightly more complex measure where we're actually considering things more like cache misses. So in various memory infrastructures, what happens is if you access a brand new part of memory that's outside of the cache, this results in a cache miss, and it's a more expensive operation to go and retrieve it from memory. So to sort of roughly approximate cache misses, what we're going to do is measure the number of non-consecutive sections that are probed. So in this case, what happens here is that the user probes 2 non-consecutive sections, so the cache locality is 2. All right, okay, moving on. The final important property of information-theoretic encryption is the rate of encryption. And what we mean by rate is how much of the private key can be used. So the optimal rate of information-theoretic encryption is essentially the simple stateful one, where essentially you utilize each portion of an unused portion of the key for each encryption. In this way, you essentially are able to use the entire key to encrypt messages. So in our work, what we really want is to design schemes with the similar rate of usage of the private key, but are both locally computable as well as stateless. For example, this solution, the one that has optimal rate of information-theoretic encryption, as we have shown, is stateful and is not useful in settings where there are many, many people who are trying to encrypt simultaneously. So in our work, we'll try to aim to solve aim for all of these 3 properties simultaneously. All right, so let's move on to something called bounded storage model extractors. So in this model, what's essentially happening is slightly different than information-theoretic encryption, but we'll show that they're very related. So at a high level, what they have is a source X, which you can imagine as some random long bit string. And then the user has a seed S. And the whole point essentially is for the user to probe some subset of the source X and compute something called the extraction from X using S. And in this model, there is an adversary, and the adversary is able to get some bounded leakage. So what it's able to do is it's able to compute some function of the source X, but typically the output of this function, of this leakage function, will be smaller than the source X. So essentially, for example, the adversary can maybe store half the bits of the source of X, but it can do it in any function it wishes. So for security, the whole point is that the extracted value of X and S should be indistinguishable from random, even though the adversary has obtained some leakage L equals F at X, but this leakage is of bounded size. And essentially, we want to make sure that with high probability, the extracted results are indistinguishable from random. All right. So what it turns out is that you can actually build information-theoretic encryption from such extractors. So it's not very complicated. So what happens at a high level is we can actually view the private key as the source X. When a user gets a message it wants to encrypt, it'll generate some random seed S, essentially run the extractor, and then what happens is it'll output 2 things as this encryption. First, it'll output the random seed S, And then secondly, it'll output the message XORed with the random extracted value from X and S. And of course, now for decryption, it's straightforward. What happens essentially is that the receiver would receive the seed S. It can again compute the extraction of X and S, and then simply XOR the ciphertext to get back the original message. So this seems to work at a high level, and it turns out the security is very straightforward to adapt as well. Essentially, what you can assume is that all the probe bits used for the encryption and decryption oracle are compromised by the adversary. And what's essentially happening is, since the adversary is viewing encryptions and decryptions in typical information-theoretic encryption, we can just use the security of the bounded storage model and assume that that is the leakage that was seen by the adversary. So it turns out the security reduction works as well. So there's a natural question of asking, like, are we already done? Are bounded storage models extractors exactly what we need? And the answer is yes and no. So bounded storage model extractors do work, but they have essentially three main issues. And let's start off with the first one of post-application leakage. So let's consider an actual game that sort of represents, let's say, in CCA1 encryption. So in this model, you sort of have the adversary who is able to do encryption and decryption oracle calls. At some point, it submits a message as a challenge, and it'll get back either an encryption of the message or a truly uniform random string. And the goal is for the adversary to determine which of the two we're getting. Either it's an encryption or a random string. If the adversary is unable to do this, then it's clear that the encryption is secure. But in typical models, after you get this message, after you send the challenge, you should still be able to have access to the encryption oracle to be able to essentially maybe potentially use the ciphertext and get more answers. Of course, you shouldn't have access to the decryption oracle, otherwise you could just send the challenge back and get the decryption. But essentially, this is an interesting part where essentially after the application, after you send the message and you get potentially the encryption, you can actually use that encryption to get more leakage. And this is what we call post-application leakage. And it turns out that for general locally computable extractors in the bounded storage model, for the natural setting where the output is larger than the input seed, it's been shown that you can't prove general security for these BSM extractors with post-application leakage. So this is a problem, because in natural settings like this, where we want to have post-application leakage, we're unable to use the BSM extractors. The second problem is this notion of computationally secure seeds. So let's go back to this idea before where we actually outsourced the key to a cloud storage server. Right? In this model, we said that all honest parties are able to query the cloud server for the key, but simultaneously, the adversary is also able to compute, for example, functions or extractions of the key. So let's go back to the original construction we had in mind, where the adversary would use a BSM extractor. It would actually send the seed S as well as the message XORed with the extraction. Well, this no longer works in this setting when we outsource the key to the server, because if the adversary would get to see the seed S, it would be able to compute the extraction using X and S, because the cloud server would sort of reveal X. And it essentially means that this is no longer secure. This is clearly not an information-theoretic encryption scheme anymore when there's a cloud storage server that exposes X and the adversary has access to it. So how we could solve this is through the use of computational secure seeds, for example. Let's suppose we use the Diffie-Hellman key exchange, where the sender and receiver do the Diffie-Hellman key exchange and are able to essentially come up with a shared private key. So then what they could then do is potentially use this. So when they want to encrypt, the two parties can expand their secret key, because we're doing computational secure seeds anyways. You can use a PRG to expand it even further, and then sort of use this as a seed. So what would happen is the encryptor or the sender would use this seed S that both parties have to get an extraction from the server, which exposes the private key X, and then simply send the ciphertext, which is an XOR of the message with the extracted value. And simultaneously, the receiver, since it has the seed S, it can also contact the server, and essentially compute the decryption and by computing the extraction. All right, so we call this notion essentially everlasting privacy. And what it means essentially is that you have sort of these dual adversaries. So when the cloud service is available, let's say we assume the cloud server is only available for a temporary period of time, we assume that the adversary is computational bounded. For example, it cannot compromise the computational seed. And then after the server is no longer serving requests, we can assume that the adversary is information theoretic and all powerful. But in this model, which seems very interesting, we are actually able to still provide everlasting privacy for the information theoretic encryption. So let's take a look carefully. What we mean is when the adversary is small and is like computationally bounded, it can still do requests to the cloud server. Of course, if it was all powerful, it could compromise the keys that the two parties share, and it would have been able to essentially decrypt already. But for example, when the adversary is all powerful and the servers are no longer available, in this setting, we can still prove that our encryptions remain information theoretically secure. So this is an interesting notion where we're able to get over the fact that the keys have large memory by outsourcing them to a cloud storage server. And in this case, you can see why computationally secure seeds can be very powerful. So sort of going back to the bounded storage model and their extractors, it has been proven a couple times by Zimbowski and Maurer, as well as Harnack and Noor, that extractors in the bounded storage model may not be reduced in a black box manner to handle computationally secure seeds. So extractors in the BSM model are unable to even be able to be used in this very interesting setting where the key is outsourced to a cloud storage server. All right, so the last thing I want to talk about are suboptimal rates. So it turns out that essentially these bounded storage model extractors don't have very close to the optimal rate, which is essentially the simple stateful solution that uses the entire key with XORed messages. And it turns out there's a very good reason why. So if you take a look carefully at the definition, even though the adversary's leakage is bounded, it's technically an arbitrary function. This function f can be arbitrary. And because it's arbitrary, it ends up being quite hard to prove that constructions are secure. And actually, this will be important for us when we go into our contributions. So what are our contributions? We essentially have like three main points. The first is that we will define the notion of something called doubly-affine extractors, which end up resolving all the prior obstacles that I mentioned above. Secondly, what we're able to do is present security reductions for these specific new extractors, where security is equivalent to essentially very simple linear algebra idea. So it turns out that proving security ends up being very clean. And finally, what we're able to do is using these security reductions, we construct doubly-affine extractors that have all these three properties of being stateless, local, and very close to the optimal rates of usage. All right, so let's get into our contributions then. So what are doubly-affine extractors? So we go back to this exact same setting of the bounded storage model. The only difference is when we consider doubly-affine extractors, we make the restriction that the extracted output must be linear in the random source. And simultaneously, we require that the leakage that the adversary sees is also linear in the source. So this seems like a weird or random restriction at first, but it turns out to be very, very natural in the setting of information theoretic encryption. And the key observation is that if you think about it, the adversary's leakage is really just the result of encryption and decryption oracle calls. So if the encryption and decryption functions are linear in the source, X, the adversary's leakage is also linear in X. So taking a look back at this NCCA1 encryption game, you sort of see that the adversary's leakage is exactly the encryption and decryption oracles. And remember that the simple reduction from extractors to information theoretic encryption was simply just an XOR of the message and the source. So by ensuring that our extractors are linear, we can guarantee that the adversary's output or the adversary's leakage is also linear. So, okay, another observation which ends up being very important is that, of course, it's very simple to construct extractors against adversaries with very structured linear leakage. Essentially, it's easier, right? Because in the bounded storage model, the extractors have arbitrary leakage, whereas here they'd be linear. All right, so now that we see why Doubly-Affine extractors are important, we're going to talk about our security reductions now. So first of all, what is the security of a Doubly-Affine extractor? Well, it's very simple. Essentially, in this game, what you sort of have is you draw a bit B, which will be which will determine whether you're sending an extracted value or a random value. You draw the random source X, you draw a challenge seed S, and then you either send the real extracted value or a uniformly random string to the adversary. So the adversary, given this sort of challenge, will be able to get linear leakage from the adversary. So it will be able to choose an XOR of some potential subset or the entire source and get back these XORs. And then finally, in the end, it'll be given the challenge seed S, no more access to the source, and it has to guess whether it was either a random string or an extracted string. And one thing I want to note is that post-application leakage is built into this because of the original message or the application is already being sent to the adversary before it gets any leakage. All right, so what is the definition of a Doubly-Affine extractor security? Essentially, we call it L epsilon secure if any adversary with at most L bits of linear leakage cannot distinguish the output of an extractor from a random string with probability at most epsilon in the above game. All right, so let's take a look at this carefully though. So since this is all linear algebra, I want to take a look at the adversary after it gets the challenge S. So once you're at this point, it seems like sort of the only thing you can really do as an adversary is check whether the linear leakage you had, the subspace that's covered by this linear leakage, does it intersect the bits that were used by the extractor? It seems like there's nothing else you can really do. And essentially, this is true. What we ended up formalizing is we reduced this game to a much simpler game here, where this adversary, essentially all it does is it picks linear leakage. It picks the bits that it wants the XORs of. And that's it. It doesn't have any more interaction anymore. And what happens is the challenger is actually able to do the check. Essentially, exactly like what we said, the challenger can determine who wins the game by simply checking if the intersection of the subspace of the linear leakage matches whatever was used by the extractor. And we actually are able to prove this formally, essentially. And as a sort of a corollary, what we're able to show is that the adversary's optimal strategy once receiving the seed S is exactly checking whether the leaked subspace intersected the extracted subspace. So this makes security very simple and straightforward now, as we're only considering linear algebra and essentially linear subspaces. So, okay, going to computational, we essentially have a very similar game. The only difference is now that for this adversary, A1 and A2, we require that A1 is essentially bounded. So essentially, what's going to happen is A1 will receive the leakage of Z, that's essentially the leakage of a computational C generator, sigma. But everything else stays the same. And once again, what we can quickly note again is that let's look at A2. Let's look at this. Now A2, remember, is an all-powerful adversary. He has absolute power, but doesn't have access to X anymore, and is given the seed as prime. The question then becomes, what could this adversary do? Okay, it could break the computational seed generator, but is that interesting? Because it's already given the seed. So once again, we're at this point where it seems like the adversary's optimal strategy is the same as the prior game, where it should just try and compare subspaces. And we are able to prove that again, actually. So we, once again, are able to prove exactly this, and we prove that that's the optimal strategy for the adversary. And in particular, what we're able to show is that if let's say the computational seed generator is epsilon prime secure against PPT adversaries, and there's a Doubly-Affine extractor that's L epsilon secure against any information-theoretic adversary, then we show that the same extractor ends up being L epsilon plus epsilon prime secure against any PPT adversary when using the computational seed generator. So long story short, all we have to do and all we have to think about is proving and constructing Doubly-Affine extractors against information-theoretic adversaries. All right, so let's get into our constructions. Our constructions will end up using the sample then extract paradigm of Vadon in 2004. So what happens at a high level is two steps. First, what we'll do is sample a subset of bits from the source X. So here we sample 4 bits. But what happens is, since we're sampling, we're not doing any computation on top of it, it's very possible that one or more of the bits are compromised and the adversary knows what those bits are. So after we do the sampling, to sort of mix the bits together in such a way that the adversary will not be able to predict any of the bits, what will end up happening is we essentially apply a non-local extractor. So the whole point of the non-local extractor is to take all the bits, combine them together, and extract as much entropy as possible. And this is the sample and extract paradigm that we'll use in our construction. So let's start off with the sampler. So the sampler is essentially just a weaker version of an extractor where you have to essentially pick the bits from the source as your output. So, okay, this seems like a weakening for the sampler, as the extractor is able to mix bits and essentially compute XORs. But what we're able to show actually is that in the sampler game, the optimal adversary is actually one who only picks bits as well. So even though we're weakening the sampler to only have to pick bits of the source's output, simultaneously the adversary can also be weakened to only pick bits as leakage, as linear leakage, essentially. All right, so with this reduction, we're able to construct a sampler, which is not very complicated, it's very straightforward. So what remember we wanted was a sampler with C cache complexity. So we only hit C non-consecutive regions, and we want to touch at most P bits. So what we essentially do is we take the N bits, we break it up into C rows, we pick a random subset of size P over C within each row, and what we're able to show essentially is that this will have cache complexity at most 2C and probe complexity at most P. And what we're able to show is the following theorem, essentially that there exists a sampler with probe complexity P, cache complexity C, seed length C times log N over C, that is L epsilon secure, and at least lambda bits are not compromised, where the probe complexity is this, that's shown here. But we can show that this is essentially almost optimal because of the probability of that the adversary sees L bits of leakage. And what we're essentially saying is that if you pick lambda over 1 minus L over N, and there's some small loss here, this is essentially the probability of sampling something that was not seen by the adversary. And this is essentially almost the optimal rate, except for this little part over here. All right, so then for non-local extractor constructions, there's a simple idea where you could just use the leftover hash lemma with linear functions, but this is bad because you lose 2 times log 1 over epsilon bits, essentially from the entropy. Well, the maximum you can extract is N minus L if there's L bits of leakage, and you're going to lose 2 times log 1 over epsilon bits. And what we end up showing is that we can actually beat this because we're considering weaker adversaries that have only linear leakage, we can only lose log 1 over epsilon bits if we consider toplets matrices, although these have slightly larger seed lengths. And we also show essentially there exists a non-local extractor with seed length log N, essentially, which is almost optimal. All right, so finally, when we combine those two together, what we end up is with a final doubly-affine extractor, where the probe complexity, if you wanted to extract M bits, is essentially M over 1 minus L over N, and with some loss on each side. And this is essentially almost an optimal rate, because essentially the optimal rate would be M over 1 minus L over N. All right, so in summary, what we're able to do is construct doubly-affine extractors that enable information-theoretic encryption with the following properties. It's stateless. Essentially, there's no state being stored. They're very locally computable, and they have almost optimal rates in the fact that you can essentially use these. Essentially, you're not wasting bits, as we showed here, where essentially, if you wanted to extract M bits, you're only using slightly more than M over 1 over L minus N, L over N, which is the optimal rate. All right, so let's talk about the two applications quickly. Remember, we said earlier that this enabled replicated key settings, and this is exactly it. Because of our constructions have all these properties, you can automatically use this in the replicated key setting. And simultaneously, because of the fact that we were able to sort of enable computation-secure keys, we can also enable this in the outsource setting where the seeds are computationally secure. So, all right, I wanted to thank you everyone for listening to this talk. And if you have any questions, please feel free to email either Yevgeniy or myself at the emails listed there. And thank you for listening to the talk again.